Hello, Professor. This is week 1, homework B, and I chose question number 5. It states a 4.7 microcoulomb point charge is placed in an external uniform electrical field that has a magnitude of 41,000 newtons per coulomb. At what distance from the charge is the net electric field 0? So, with the net electric field being 0, we can conclude that the electrical field due to point charge, the magnitudes, are equal to each other. So we can just be able to find, or we can just be able to use this formula and plug in to be able to get R, the distance. So E is the electrical field due to point charge magnitude, and this is the SI unit is newtons per coulomb, and this is also a vector, which is why I've written it in a vector form. And the book states that when it is 0, then we do have this, where E1 equals E2. And up here I've demonstrated that in the beginning we had an external charge already, and then we added another point charge, and we want to conclude where what the distance is for when it equals 0. So this just means that when these two points equal each other. So yeah, we're just able to go off of this equation. And so the K in this equation would be electric constant 9 times 10 to the 9th, which is Coulomb's constant. And the SI units for this is newtons times m squared, which is meters, divided by Coulomb squared. And Q is the value of point charge. And the SI units for this is just coulombs. And this would be where we place our separate charge at, because in this in the problem it says the 4.7 microcoulomb point charge is placed in an external uniform electric field. So that means that we already have an electric field happening, and then we place this Q point here, which already has, would be its number. R, like I said before, is the distance from point charge to where the field is measured. And so that is demonstrated in meters. And that is in here in our equation. And this whole equation is electric field due to charged particles equation. So in the formula, it gives us, now it's basically just like a plug and chug. And, or in the problem, it gives us the Q in microcoulombs, but in order to put this into the equation, we need to convert it to coulombs. So I know that 1 microcoulomb equals 10 to the negative 6 coulombs. So we just convert 4.7 microcoulombs times 10 to the negative 6 would be 4.7 times 10 to the negative 6 coulombs. And then we have our E already, and we want to know what R is. And then we have our K, which is just the constant that is universal. So we have our equation E equals KQ divided by R squared. So in order to get R by itself, I multiplied R to get it over here, and then I divided the E to get it over here under the K and Q. And then finally, to get R by itself, you have to square root the whole thing. So this whole equation is going to be square rooted. So now I just plugged it in, and here you can see that, let me get a marker. Oh, here we go. So what's going to cancel out is, this is the K constant. The newtons are going to cancel out. It'll go away. But and then our coulombs are going to cancel out. So it makes sense that we're left with just our m squared. And then once we get, or that m squared is going to be square rooted, so we're just going to have 1m. And then we're going to get this whole number as the final answer. So the distance to where the whole net charge is 0 would be 1.02 meters.